Hey everyone, and welcome to this explainer. Today we're taking a look at a genuinely groundbreaking theoretical physics paper that is actively challenging, well, pretty much everything we thought we knew about the fundamental nature of the universe. You know, for decades, the absolute holy grail of modern physics has been finding a theory of quantum gravity. We've been desperately looking for a way to unite the massive scale of the cosmos with the microscopic, jumpy world of quantum mechanics. But what if we've been looking at it completely backwards? Today, we're unpacking a radical new framework proposed by physicists Jonathan Oppenheim and Zachary Weller-Davies. And I've got to tell you, it's a concept that might just rewrite the textbooks entirely.
Okay, let's dive into this. For the better part of a century, the basic assumption has been that because matter is fundamentally quantum, gravity must, by definition, be quantum too. I mean, think about it. Millions of hours of intense research, incredibly complex string theories, loop quantum gravity models, they've all been built on this single foundational premise. But what if the biggest hunt in modern physics is actually just a wild goose chase? What if gravity absolutely refuses to be quantized because it simply doesn't need to be?
Section 1. The Gravity-Quantum Clash.
To really grasp why this new theory is such a massive game-changer, we first need to look at the fundamental incompatibility between our two best models of the universe. On one hand, we have general relativity. This is Einstein's masterpiece, right? It describes classical spacetime as this smooth, predictable, continuous fabric that bends and warps. It's beautiful. But then, on the other hand, we have quantum mechanics, which describes matter as probabilistic, jumpy, and totally capable of existing in multiple states at once, which we call superposition. The problem, as outlined in this new paper, is incredibly simple but devastating. When you try to put quantum matter into Einstein's field equations, the math literally just breaks down. One side of the equation is a standard number, and the other side is a quantum operator. Trying to combine these two systems is exactly like trying to run modern macOS on a vintage typewriter. They just do not speak the same language.
Section 2. Breaking the physics rules.
Now, what's really interesting about this is what happens when scientists try to force these two completely incompatible languages to communicate. Historically, they just hit a massive brick wall. We're talking about famous no-go theorems, championed by brilliant minds like Richard Feynman as well as Epley and Hanna. They mathematically argued that coupling classical gravity with quantum matter would result in physical impossibilities. They believe it would completely destroy quantum superpositions, or worse, allow for superluminal, meaning faster-than-light signaling. No way, right? Those incredibly powerful arguments created the widespread, deeply entrenched belief that gravity must, for sure, be quantized.
But, as you know, in physics, there's always a new angle to explore. Enter the secret weapon of this new paper, stochastic coupling. This is a statistical loophole discovered recently that basically acts like a universal translator between the classical and quantum realms. It actually allows us to bridge the gap without breaking the fundamental laws of probability. What that means is the system can exist as a distribution over classical degrees of freedom, perfectly combined with a density matrix in the quantum space. Essentially, it allows classical and quantum systems to interact consistently, maintaining positive probabilities without violating a single one of those old no-go theorems we just talked about.
Section 3. Post-quantum classical gravity.
And this brilliantly illustrates how the radical new math actually works. Take a look at the classical quantum or CQ dynamics. The authors have formulated this master equation that perfectly blends the transition probabilities of classical dynamics with the quantum operations of the quantum side. Those are the Krauss decompositions, which are essentially just the mathematical rules for how quantum states change. You can see how the positivity and norm conditions in the new CQ model naturally generalize the rules from both of its parent theories. It's this incredibly elegant, mathematically consistent hybrid that ensures all the probabilities remain positive and sum up exactly right.
So let's break down the core components of this post-quantum theory. We know it effortlessly circumvents the old no-go theorems and totally bypasses the weird pathologies of older semi-classical gravity models. Plus, its dynamics are wonderfully linear in the density matrix. But, and this is a big but, there is a major trade-off. In order to keep gravity entirely classical, quantum mechanics itself has to be slightly modified. This theory actually necessitates fundamental information loss, and the intense interaction between the classical and quantum layers causes the decoherence of quantum fields. It's definitely a bold compromise, but hey, it's one that makes the math work.
Section 4. Testing the math. Proposing a bold new idea is one thing, but if you're going to challenge a century of physics, it has to survive some pretty extreme scrutiny. To rigorously stress test this, the authors utilize something called the Dirac argument. Here's how it conceptually works. In Einstein's general relativity, you have this concept of gauge freedom, represented by lapse and shift functions. That basically just means the physics shouldn't change depending on how you arbitrarily slice up your time and space coordinates. So the authors test their new CQ theory by defining this freedom, running their master equations of motion,
and checking if the mathematical algebra neatly closes. In simple terms, they're testing if their mathematical bridge holds up when the highly unpredictable quantum wind blows against the flexible fabric of classical space-time.
So the crucial point is that to preserve Einstein's rules of space-time flexibility, which is known formally as spatial diffeomorphism invariance, the authors discovered they must satisfy generalized structural constraints. They derive a CQ analog of the momentum constraint, and preserving that over time gives them a CQ analog of the Hamiltonian constraint. They are quite literally mapping the foundational, rock-solid rules of classical gravity right onto this brand-new hybrid framework.
However, they do hit a bit of a mathematical hurdle here. Actually, scratch that. It's more like a fascinating open puzzle. When running the calculations for a quantum scalar field interacting with classical gravity, the algebra doesn't perfectly close all on its own. It reveals these anomalous terms. This means that for the theory to be perfectly consistent, we either need to discover additional constraints that the universe obeys, or we have to accept a smaller gauge group, meaning we must place specific physical restrictions on exactly how we choose our lapse and shift functions. It's an incredibly cool open problem that the researchers are continuing to explore right now.
Section 5. The future of space-time. Let's move to and see how this builds into something even bigger.
Because it's time to step back from the intense mathematics and look at the massive, absolutely universe-altering implications of this research. As highlighted by The Guardian in our source material, this isn't just some abstract mathematical exercise. This controversial new theory of post-quantum classical gravity potentially rules out the need for dark matter entirely. Think about that. For decades, we've observed galaxies spinning way faster than they should based on the visible matter they contain. To put that into perspective, it's like watching a merry-go-round spin so fast the kids should be flying off, but they don't. So, we invented invisible dark matter to balance the cosmic scales. But if space-time is actually a classical quantum dynamic experiencing this stochastic, jumpy interaction we've just learned about, well, that very interaction might effortlessly explain the universe's missing mass, solving one of our biggest cosmic mysteries without needing dark matter at all.
And that brings us to our final thought. For almost a century, we have just assumed we needed to force gravity into a tiny quantum box. But by letting gravity remain classical and allowing it to mathematically talk to the quantum world through stochastic coupling, we might just unlock a completely new understanding of reality, from the bizarre behavior of black holes all the way to the dark matter illusion. It leaves us with a thrilling question. If space-time isn't quantum, what other secrets is the universe hiding in plain sight? Thank you so much for joining me for this explainer. Keep questioning, keep looking at the data, and I'll see you next time as we continue to unpack the fascinating structures of our world.